So let's do an example. This is the function we're going to analyze and find the Fourier series of. It's kind of a square wave. It starts at 0 and then jumps up to a value of 1. So there's a discontinuity here. And this will be periodic when we calculate our Fourier series, and so the function will continue on like this. And it's defined formally like this. It's 0 between x is 0 and a half, and it's 1 when x is between a half and 1. So the periodicity here is 1 in these arbitrary units, so lambda is equal to 1 and u0 is equal to 1, just to make things simple. What can we notice about this function without doing any maths? Well, the function has an average value of a half, and so that means that a0 on 2 must be equal to a half. In other words, a0 must be equal to 1. So almost with no maths anyway, we've already calculated one of our coefficients. Another thing you can notice is if we subtract that value of a half, then what's left over is a function that will be odd. And if the function is odd, then we know that for all an, for n greater than 1, an must be equal to 0. So we'll only need to calculate the bn's to get the Fourier series in this example. So, like I was explaining before, these are things you can, if you look at the function first, you may be able to simplify your problem quite a lot. Okay, so here's the example. There's the function. We recognize that lambda is 1 and u0 is equal to 1. And so the equation that we need to figure out here is the equation for bm. So the equation for bm will be the integral, twice the integral from 0 to 1, that's the period here, f of x sine 2 pi mx, and u0 here is equal to 1, as I've said. So this must be equal to, if we substitute now in the expression for f of x, because you know what f of x is, this must be equal to the integral from a half to 1 of sine 2 pi mx, because between 0 and a half, the function is 0. It's only specified as being non-zero between a half and 1. In that case, it's 1. So f of x here is equal to 1 over this domain. So we've just got to compute that integral there. And so we can integrate up this function sine 2 pi mx, and we integrate it and get negative of 1 on 2 pi m cos 2 pi mx. And then we want to find this integral of this domain from 1 to a half. And we can do that. We get this expression here. And so this looks a little bit tricky, but that's the expression for bm, for all m greater than 1. And we can simplify it a bit as well, and recognize it's actually equal to 2 on lambda times m for just odd m. a0, as we've said before, we've already established what it's going to be, but we can do it formally here and see that a0 must be equal to 1. And am, as I've already said, because we've looked at the function and decided that it is odd, this must be equal to 0, but we can prove it formally by substituting in f of x and then integrating this thing up. And so when we integrate cos, we get this sine function here, which we then evaluate between 1 and a half, and this is equal to 0. Okay, so our intuition was correct. The function f of x then can be expressed as a half minus, we have the minus sign here, the sum over 2 on pi times the odd values of an integer here, from n equal 1 to infinity, sine 2 pi 2n minus 1 times x. So this is for odd m here, and I've just rewritten this sum here for odd integers. So there is an example. We've now expressed f of x here as an offset plus a sum of sine waves. So what does it look like if we take these terms that we've calculated and start adding them up? Well, here's an example. So this is the n equal to 0 term here, just the constant offset at a half. And this is our square wave that we're going to approximate. Let's add the n equal to 1 term. So the n equal to 1 term here is in green. That's the green term here, and we add that to the offset and we get the red curve here. We'll add another term. This time we're adding this orange line. That's what we're adding to the other terms. We add that and add up now the orange term, the green term, and this blue term, and we get this resultant red. I've plotted the red here outside the interval from 0 to 1, so you can see what it looks like once all of these terms here start adding up, because it's going to get kind of messy. So I'll add a few more terms here. Frequency's getting higher, period's getting shorter, and you can see the amplitude of each successive higher frequency term gets smaller and smaller. And now this red curve here is starting to look a lot more like the square wave that we're trying to approximate. Let's just run this animation and add up all the terms to n equals 100. And we can see the red curve gets more and more like a square wave as we add these terms up. We can also see there's some overshoot here. There's a bit of an error in this approximation, and we'll talk about that in a second. But here are the takeaways that we can begin with. More terms gives a better approximation. So as you add terms, the approximation gets better and better. So here we are adding the terms up again, and you can see you get closer and closer to the square wave as you add more and more terms. There's the overshoot. Now this is known as the Gibbs phenomenon. For a step discontinuity, which is what we have here, the overshoot is 9% on each side of the step. So we go from 0 and we jump up to 1, and the offset here is about 9%, and we have 9% on this side. So the total discontinuity here is 18%, if you like. And as you increase the number of terms, the width of the overshoot tends to 0, but the amplitude remains constant. So the integral of the error, if you like, will tend to 0, but the amplitude here will always be 9%. And the Fourier series is periodic. In this example, the period p is equal to 1, or lambda, as I used before, is equal to 1, and the lowest frequency term in the Fourier series also has that period of 1. So there's the lowest frequency term. A final way of visualizing the creation of a square wave from its harmonic components is like this. What we've got here are 3 circles, and we're going to draw phasors that rotate around these circles at different speeds. So the blue's the slowest and green's the fastest. They have different radii, so when we project the vertical displacement over here onto this graph, we have 3 different sine waves of different heights. And they are related in the following way. So they are the odd harmonics, with amplitudes decreasing as 1 on the frequency. And there's a black one here we're adding in as well now. Now what we're going to do is add them up. So we take all of the phasors out and then add them all up. Instead of showing them all on top of each other, we start adding them up, and including this 4th black one. And then they all rotate around different frequencies. The black one 4 times faster than the blue one. And we see sometimes they all add up constructively, and that's where the Gibbs overshoot occurs. And other times they act up sort of maximally destructively, which is where it passes through the minimum in this Gibbs overshoot here. And as you can see in these first 4 terms, we get this approximation to this square wave. Now the amplitudes here, if you look carefully and compare this with the example I did before, the amplitudes of each of these terms here is different, because now we're going from 1 to -1. And also there's no constant term, because the average of the square wave now is 0.